acephysics.org. All right, we're going to do a video on vectors. This is going to be vector addition, vector subtraction, adding vectors graphically as well as in component form. So let's learn about vectors. They're very important in physics. I love physics. All right, so here's a quick overview. We're going to define a vector and a scalar quantity, finding the components of a vector, adding and subtracting vectors graphically, adding and subtracting vectors in component form. There will be a couple of example problems on this presentation, and then there will be some following presentations which have more problems. To begin with, what is a vector? So first of all, vectors are one of the most important mathematical tools in physics. They are used to represent motion, wind flow, weather patterns, forces, velocity, current, and many other quantities in physics. A vector is an arrow in space. Here's vector A, and here's vector B. A vector has a tail and a tip. The tip is where the arrow is. The tail is where the arrow is not. The vector has a magnitude. The magnitude tells the length of the vector. So in this case, vector A has a smaller magnitude than vector B. A has a smaller magnitude than vector B because it has a smaller length than vector B does. There are vector quantities in physics and there are scalar quantities in physics. A vector has both a magnitude and a direction. As I said before, magnitude tells the size of something. A scalar only has a magnitude. Here's some examples of quantities in physics, and let's decide whether they're vector or scalar quantities. To begin with, time. Is time a vector or scalar quantity? What do you think? Time is a scalar quantity because you say it's 4 o'clock. You don't say it's 4 o'clock going north, or it's 4 o'clock going backwards. Temperature. Temperature is also a scalar quantity. You just say it's 82 degrees outside. Now you might say, well, there's global warming, so it's 82 and rising. But, global warming just means if you move to Arizona, you can barbecue your chicken without a grill. Velocity is a vector quantity. The reason velocity is a vector quantity is because you say something is going 25 meters per second to the south or 25 meters per second northeast. It's got to have a magnitude, which is how quickly it's going, as well as a direction. Acceleration is also a vector quantity. What about force? Force is a vector quantity as well because something can be pulled up or down or to the left or to the right. And price is a scalar quantity. So these are the three vector quantities, and I put arrows next to them because a vector is an arrow. There's something called vector nomenclature. So you need to be able to describe a vector. And you can do that one of two ways. And the first way is in angle magnitude form. So if you give the magnitude of a vector and the direction or the angle, then that's one way to represent a vector. Here is north, east, southwest. Never eat shredded wheat. This is a vector that has a magnitude of 12 meters and it's directed 60 degrees north of east. So first of all, the magnitude of the vector is 12. That means it has a length of 12. And if you start east and you move 60 degrees towards the north, then you end up at the vector. So it's 60 degrees north of east and its magnitude is 12. The units are meters because this is a displacement vector. If it were a velocity vector, its units would be meters per second. If it wasn't a force vector, its units would be newtons and so on. Here is another vector. You may want to pause the video right now and see if you can write down and see if you can describe this vector in angle magnitude form. What is the magnitude and direction of this vector? The magnitude is 19 meters because that's the length and that's given. And the direction is 55 degrees north of west. You start out west and you move 55 degrees north and then you end up at the vector. In order to do vector problems, you need to know some basic right triangle trigonometry. Here is a right triangle. The hypotenuse of the triangle I've labeled V. That's because in physics, when you're dealing with vectors, the magnitude of the vector is always going to be the hypotenuse of the triangle. Here's an angle theta. This side I call y, this side I call x. Sine of theta is opposite over hypotenuse. So here's theta. Sine of theta is opposite, which is the y, divided by the hypotenuse, which is the magnitude of the vector v. Cosine of theta is adjacent over hypotenuse. So this angle theta here, adjacent to the angle theta is x. Cosine of theta is x over v. This tells us that x is equal to v cosine of theta. Y is equal to v sine of theta. And then there's the Pythagorean theorem, which comes up quite often, which is v squared equals x squared plus y squared. The magnitude of the hypotenuse squared is equal to the sum of the squares of both sides of the triangle. In physics, vectors are written in component form more often than they're written in angle magnitude form. They're written in both. You need to know both, but component form is more common. So to write a vector in component form, first of all, there are unit vectors assigned with x, y, and z. So here's a 3D Cartesian coordinate system. The x corresponds to the I hat. So an I hat is a unit vector in the x direction. I just corresponds to the x direction. This is the standard nomenclature. The y direction is j or j hat. And for z, k or k hat corresponds to the z direction. I'm going to mainly work in 2 dimensions for this presentation because adding in a 3rd dimension just introduces unnecessary complications. Here's a vector v. Let's write this vector v in component form. V has 3 units in the x direction. 1, 2, 3. So there's 3 I hat. And this little hat above here, oftentimes it's written as kind of a triangle without the base, but this I means the unit vector I hat. 3j or j hat is the magnitude in the y direction, 1, 2, 3. So this vector v is 3i hat plus 3j hat. The magnitude of v is the square root of the x component squared plus the y component squared. The magnitude of v equals the square root of 3 squared plus 3 squared, which equals 3 root 2, and that's the length of this vector v. Here's another example of writing vectors in component form. Write the vector v in component form when the magnitude of v is 10 and the angle is 30 degrees north of west. Here's the vector v. Here's the angle theta. So the magnitude is 10 and the angle theta is 30, and it's as shown in this picture. The x-coordinate is how long the vector is in the x direction. That's this length right here, is v cosine of theta. And for this particular problem, that's 10 cosine of 30. And the y component is v sine of theta, which is 10 sine of 30. Now notice that the x direction points in the negative direction and the y direction is positive. So you need to be careful to add in the negative sign yourself. 10 cosine of 30 is 8.66. And you need to add in the negative sign simply by looking at the vector and seeing that the x component of the vector is negative. Here's an example that you may want to work on. You can hit pause on the video right now. Write the vector v in component form when the magnitude of v is 25 and the angle theta is 20 degrees south of west. So first of all, just for the nomenclature, here's the angle theta. You start at west and then you move 20 degrees and then you move 20 degrees towards the south. Now this isn't, obviously it's not drawn to scale. So the answer to this problem, the x component is v cosine of theta, which is 25 cosine of 20. The y component is v sine of theta, 25 sine of 20. And notice that both the x and the y component are negative. In quadrant 1, this is quadrant 1, both x and y are positive. In quadrant 2, y is positive, x is negative. In quadrant 3, both x and y are negative. And you can see that this vector, it points in the negative x direction and then the negative y direction, and that's the vector v. So the vector v in component form is negative 23.5 I hat minus 8.55 j hat, and the vector v in angle magnitude form is the vector v has a magnitude of 25 and an angle of theta equals 20 degrees south of west. So we've covered what a vector is and how to write vectors in component form and in magnitude form. The next thing you need to know in physics is how to add vectors graphically and also how to add vectors in component form. So first I'll just read through the steps of how to add vectors graphically, and then we'll go through some example problems to make it more concrete. So you start at the origin and you draw each vector to scale with the tip of the first to the tail of the second, the tip of the second to the tail of the third, and so on. Then you draw the resultant vector. The resultant vector is the addition of all the vectors, and the resultant vector starting from the origin and ending on the tip of the last vector. The tip of the resultant vector should touch the tip of the final vector, and the tail of the resultant vector should touch the tail of the final vector. Now let's look at an example of adding vectors graphically to get a more concrete understanding of how this works. A chihuahua, or as I like to call them, a chihuahua, walks 7 meters east, then she turns 30 degrees north of east and walks 4 meters. Finally, she walks 1 meter north. Find the resultant displacement vector graphically. All right, so first of all, the chihuahua walks 7 meters east. Then she turns 30 degrees and walks 4 meters, and then she walks 1 meter. So the way to add vectors graphically is you first write down the first vector. And notice it's to scale, so 7 meters would be longer than the 4 meter vector, which would be longer than the 1 meter vector. So 7 meters east. Then you take the second vector and you put the tail of the second vector on the tip of the first vector. And then you take the third vector and you take the tail of the third vector and put it on the tip of the second vector. And then the resultant vector, the tail of the resultant vector starts on the tail of the first vector, and the tip of the resultant vector ends on the tip of the last vector. So the addition of these three displacement vectors is equal to r. R is the answer. This vector r is the answer. It is the resultant, which is the sum of the three displacement vectors. That was an example of adding vectors graphically. You also need to know how to add vectors in component form, and in fact, it's probably even more common and more important. Here are three vectors, v, a, c. V is equal to 3i hat plus 3j hat. A is equal to 2i hat plus 7j hat. C is equal to negative 1i hat minus 4j hat. In order to add vectors in component form, you add all the i hat components together and all the j hat components together. V plus a plus c equals 3 plus 2 minus 1i hat. 3 plus 2 minus 1 plus 3 plus 7 minus 4j hat. You add up all the components in front of the j direction. And so v plus a plus c is equal to some other vector, k. K is just a random name. It can be anything you want to. You call it whatever you want to. It's just some new vector. And this new vector k is equal to 4i hat plus 6j hat. Okay, now let's come back to the previous problem that we were looking at with the chihuahua. But now let's analyze this problem in terms of component form. So write vectors a, b, and c in component form. Add a, b, and c together to get the resultant vector r, again in component form. The first step is we want to be able to write these three vectors in component form. So notice that vector b has both an x and a y component. Vector b has an x component as well as a y component. And the x component is the magnitude times cosine of the angle. So it's 4 cosine of 30i hat plus 4 sine of 30j hat. They're both positive. Vector a is equal to 7i hat plus 0j hat. Vector a only points in the x direction, and so it's 7i hat. There is a 0j hat, but it's unnecessary to write that term. Vector b is 3.46i hat plus 2j hat. That comes from this equation up here. And vector c is 0i hat plus 1j hat. Once again, it's not necessary to write the 0i hat, but if you're seeing this, if you're just learning this, it's helpful to do it for the first couple examples. So the question is, now we want to find the resultant vector. So to find the resultant vector r, you have to add up the three vectors a, b, and c, and in component form. And to do that, a plus b plus c equals 7 plus 3.46 plus 0i hat plus 0 plus 2 plus 1j hat. There's a 0 in both one of these terms, so we left that off. So that's a plus b plus c is the resultant vector r, and that's equal to 10.46 I hat plus 3j hat. This is adding the vectors in component form. Find the magnitude and direction of r. So now we know r in component form is 10.46 I hat plus 3j hat. Now let's convert it from component form to magnitude direction. To find the magnitude of r, you take the square root of each one of the components squared, square root of 10.46 squared plus 3 squared, and then the angle theta, tangent of theta is equal to opposite over adjacent. So if you notice, this vector r moves out 10.46 units in the x direction, then it moves up 3 units in the y direction. So theta is equal to opposite, tangent of theta is equal to opposite over adjacent, which says theta is equal to the inverse tangent of 3 over 10.46. And the resultant vector r has a magnitude of 10.88 with an angle of 16 degrees north of east.